In this video, we're going to talk about how you can know if two sets of means are different. When you have two treatments, you may want to compare them to see if the two means are different. The test that can do this for you is the student's t-test, most commonly referred to as the t-test. What the t-test does is compares the difference between the two means, which is your signal, weighted by the variation in the data, the noise in the data introduced by natural variation and error. The figure here can be used to explain this. Each set of graphs here is simplified frequency histograms. The x-axis is the value of the dependent variable, and the y-axis is the number of observations of each value. The two colors represent two different treatments. In all three graphs, the means for each treatment are the same, but the variation around the data are different. The signal we are interested in is the difference between the two means. The noise is the variation around the mean. On which graph, medium, high, or low variability, is it easier to see the difference between the means? For most, the graph that has the lowest variation has the strongest signal. It is easier to see the difference between the means on that graph. Thus, when we are comparing two data sets, it is necessary to determine how big the signal needs to be in order to say that the means are really different from each other. That's what the t-test does. When you do a t-test, you're asking the question, is there a significant difference between the two means? Another way to ask that question is to say, what is the probability of getting a difference between the means that is this size just by chance? The results of the t-test allow you to report that probability and to determine if the means are significantly different. When you conduct any statistical test, you actually test a very specific hypothesis, the null hypothesis, which is symbolized by HO. In the case of the t-test, the null hypothesis is no significant difference between the means. The alternative hypothesis is either the means are different, or the mean for group 1 is larger or smaller than the mean for group 2. The difference between those two alternative hypothesis statements will be important later on. Now look at the equation for the value t observed. This is what you will calculate. The numerator of the equation expresses the difference between the two means. That's the signal you are interested in. The denominator represents the noise in the data. It is the variance weighted by the sample size, n. When the square root is in the denominator, because the variance is a squared value. When you calculate t observed, do not square the variance. It is already squared, and it is written as s squared. Once you plug the values into the formula, you will get a single number back, t observed. Let's think about what that value means. If the signal, the difference between the means, is large compared to the noise, you will get a t observed that is large. If the signal is small compared to the noise, you will get a value that is small. Thus, the magnitude of the t observed can be used to determine how different the means are when standardized by the variation in the data. The exact size of the value doesn't tell you much, but people who are interested in this have figured out how big t observed needs to be in order to answer the question, is there a significant difference between two means? Excel has a t-test function that you can use, but it only reports back the significance of the t observed value. It doesn't report t observed value directly. We want you to provide that information, so don't use Excel to calculate t-tests for you. Instead, use Excel to get the mean and the variance, and then set up a formula in Excel to do the t observed calculation. It's probably worth setting up an Excel file that only does t-test calculations, and we can work on that in lab. Say that you have calculated a t observed and now want to answer the question, is there a significant difference between these two means? To do that, you compare your observed t with the theoretical distribution of t values given in a t-table. An example of a t-table is on the right side of the slide. Before you can do that, you have to determine a couple of other things. First is degrees of freedom, symbolized as df. Sample size will have an effect on the theoretical distribution of t observed values that you compare your value to. To account for that effect, you use the correct row in the table for that degrees of freedom that applies to your data. For the t-test, the formula is sample size for group 1 plus sample size for group 2 minus 2 equals degrees of freedom. Remember, sample size is symbolized by n, so it's n1 plus n2 minus 2. Secondly, you have to decide what probability you are going to use to determine the significance. In science, we commonly accept 0.05 as the highest probability that we are willing to accept to say that the two means are significantly different. While this is the common standard, it is not a rule. Note that the table can be used to report significance with other values. In the table, each column represents a different probability. The final thing you need to know to use the table is the tailoredness of the test, and that's where the two possible alternative hypotheses statements apply. Remember in the previous slide we said that there were two possible ways to express the alternative hypothesis. Either the means are different, or the mean for group 1 is larger or smaller than the mean of group 2. If, before you do the experiment, you have no way to predict which treatment will have the larger mean, you use the first version of the alternative hypothesis. The means are different. In this case, you're doing what is called a two-tailed test. If you can predict which treatment will have the larger mean, again, you have to do this before you begin the experiment. You have a one-tailed test. In the table, one-tailed and two-tailed tests affect which column of values represent which probability value. Let's take an example to show you how to use the table. Suppose you have a study where you are comparing two drug treatments to lower blood pressure. Prior to beginning the study, you know that treatment 1 is very similar to a well-known drug, but treatment 2 is completely novel. Thus, you might expect that treatment 1 would lower blood pressure better than treatment 2. Thus, you have a predicted direction of difference for the means and a one-tailed test. Sample sizes are 15 in each treatment, so your degrees of freedom is 15 plus 15 minus 2 equals 28. You're going to set probability at 0.05. You calculate a t observed of 3.5. T critical from the table is 1.701. Degrees of freedom 28. Probability 0.05, one-tailed. Thus, you could reject the null hypothesis and conclude that the means are significantly different, with the mean for group 1 being larger than the mean for group 2. If the t observed was less than 1.701, you would accept the null hypothesis. Given this example, you can actually show the reader that you have greater certainty. If you look at the row for degrees of freedom 28, you see you can reject the null hypothesis at 0.05, 0.025, 0.01, 0.005, and 0.001, but not for the last column, 0.0005. Thus, you should report in your results that you can reject the null with the probability somewhere between 0.0005 and less than 0.001. We've written that information, how you would write it, in a lab report at the bottom of this slide. Note the information that's presented, t observed, degrees of freedom, your probability range, and whether it was a one-tailed or two-tailed test, and the order that it is presented in. This should be followed in your work.